been in the industry for about 14 years, worked in airline revenue management for about 8 years, worked for a few major airlines in the US, and then did consulting and kind of analytics, if you will, operations research for airlines around the globe. And then I moved to Amazon and did retail demand forecasting for about 3 years. Did some general machine learning support, if you will, or statistical support as well, like in Amazon Prime, for example. And then I joined Microsoft, and there for about 3.5 years. I worked in Azure, doing cloud computing, doing capacity planning and forecasting. Worked in Microsoft Office, doing COGS, financial planning and forecasting. And then finally, came to Josh's team, MD ATP. So you could see, done a lot of forecasting. So kind of time series is my bread and butter. And what I'm going to talk about today, so first of all, just a caveat, not a cyber guy. If you have any detailed cyber questions, I'm not going to be able to answer them. In fact, my talk is meant to plug into cyber, but it's meant to be an abstraction of that. This should apply to any type of anomaly detection system. So with that, just quickly, go over a little bit of the topics I'm going to talk about. First, I'm going to motivate the problem. So Josh introduced kill chain anomaly detection. He talked about we have all these scores, billions of scores, right? Even more. And we're going to combine these scores in some way. And eventually, we're going to either threshold the scores, create alerts that get sent to the SOC, or we're going to generate a ranking that gets sent to hunters, right? Either way, ultimately, we're thresholding. And Josh talked a little bit about calibration. I'll properly define what calibration is. And then I'll talk about calibration doesn't need to be useful, right? Quick toy example. Imagine that we're getting these billions of scores, right? Okay, so somebody sends us a score. We don't know from where. We don't know what data generating process they're modeling. It's just a signal. Suppose they just generate numbers from a uniform distribution. Okay, that's going to be uniform. Is that going to be useful? Probably not. So my talk's going to be about how do you actually convert scores into useful scores for the purpose of anomaly detection, including heuristics. And then if I may, so the way I look at it, for those of you who know a little bit about forecasting, a big thing these days in forecasting, kind of state of the art if you will, is MetaLearning. So it's also a big challenge in forecasting to figure out what model should you use, right? Let's say there's a lot of people who are interested in LSTM these days, deep learning doing all the thinking for you. And they do have the successes in certain places, but they're not enough. So then MetaLearning is essentially, how do you have a layer on top of the modeling process? You're not doing model selection. You're not even doing ensemble learning. You're basically replicating what the statistician is doing in terms of motivating the model. What model class do you even consider? That's kind of MetaLearning. So I'm going to talk about that. I'm going to talk about two kind of applications of not even application, tasks. Two tasks for MetaLearning. One will be monitoring. So in this case, we're going to be monitoring anomaly scores. The other will be on updating scores. So remember Josh had that little sum, weight, WI. So the updating will be talking about the WIs. And then I'll give you an actual real life application. So most of this is going to be an abstraction. So yeah, I might bore you guys, you might fall asleep. I suppose the thing you should take away is how do you start with a problem, right? Like I'm giving you an anomaly score. You want to come up with a useful score. How do you abstract that? You know, what's the mathematics behind that? So that's what I'm going to focus on. I'll go into an application where I actually applied this at Microsoft and generated some successful results, so it's not just pure rubbish. And finally, I'll come up with a conclusion. There's a lot of extensions we're thinking about, research, collaborations. So yeah, that'll be the talk. I'm kind of a slow talker, and you'll quickly find out I ran very dense slides. So I've been told by several people, you could either read or you could listen. So I expect a bit of both. I'll talk a little. You could stare at the slides. I believe we'll give you the slides, okay? So anyway, let me kind of talk about the background, the motivation for this. So we're thinking about this kill chain anomaly detection system or anomaly detection system. We have these billions of scores. And so first of all, scalability is a big deal, right? As Josh talked about, we might be able to do some bivariate, some joint likelihood modeling, a lot of univariate modeling. He mentioned we're assuming IID sometimes. Okay, so the models are going to be misspecified, right? The scores that you're going to generate probably aren't optimal in some sense. So first thing to think about is, as we're passing suboptimal scores, whatever that is, some of them might even be random, what's going to be the impact when we combine these scores to ultimately produce an alert? Okay, so one impact, practical impact, would be waste people's time. You generate a lot of alerts, too many FPs. You burn bridges, they don't trust you. They go to another competitor. We don't want that, obviously. So that's what I mean by useful. Keep that context in mind. What are they actually doing with the anomalies? In cyber, well, Josh already talked about this, but quickly, we have the threat hunters, and we also have the SOC, right? And they're getting either scores or alerts from us. So think about, how do we generate accurate, or I'll just call useful, output from these? Now here's the challenge. We have heuristics. We have machine learning based detectors, which just give you like distances. They could be anywhere from -infinity to infinity. They could be ranked differently. The lowest doesn't necessarily mean the weirdest. Maybe the highest is the weirdest, okay? We also have anomaly detection scores that are probabilistic, p-values. How do you get all these different types of scores? Some are correlated, some are random, some are very accurate. We want to weight them more. How do you take all of this and create a composite score that ends up with a useful result? That's kind of the challenge, if you will. So I broke it into, what I mean by consistency is, eventually everything should be normalized, or the model you're passing the scores through need to be able to understand what they're combining, right? And then finally, once you've done all that, if you're getting purely noisy signals, meaning after you do the combining, there's no incremental value add. It doesn't help you in minimizing FPs or FNs. Okay, well then we need to have a feedback mechanism. We need to do something about this. But keep in mind, these scores could come from anywhere. We might not be able to directly communicate with the people sending the scores. Certainly we won't be able to get their exact data, what they were modeling. So that's kind of the challenge. I'll go into what you could think about as calibration. There's a few flavors. I'll give you one classic one. Josh already mentioned this. So you think about, you have some statistical model, which is basically you have a data generating process. That data generating process is providing one or more signals. You hope those signals are useful in detecting in cyber a bad guy, right? Okay, so there's different ways you could compute a statistic from a probability distribution. One is p-values, right? The predicted p-values under the null. Now, if you believe in your model, you know, there's a true model basically, it's correct, then per Josh, probably integral transformation, you guys are probably familiar with that, it should be uniformly distributed. That's not exactly true. That's true for continuous distributions. You actually have to do a little bit with highly discrete distributions, right? You're not gonna get exactly a uniform distribution scores out of it. You have to apply like jittering, for example. Handle the discreteness. Well, let's say you do all that. I have kind of a depiction here. You're gonna get few of these from me, unfortunately. So again, it might be a little boring, dry. But let's say these are the actual scores. So let's say we fix the data generating process at something, right? Maybe these are a bunch of machines and we're looking at something like port scan signals. We generate scores. Okay, and these scores, let's say they're probabilistic, they're p-values. They live between 0 and 1, with 0 being the most anomalous in our case. These are bad, right? Relative to how we modeled it anyway. Okay, these don't look very uniform, do they? But that might be okay, as I said. If we're dealing with a highly discrete distribution, you're not going to expect it to be uniform. Certainly you're not going to expect it to be uniform under a given sample. So what do? Calibration essentially maps this to a uniform distribution. It's just as it flattens it. There's different ways to do this. Quantile binning is probably the simplest way to do it. But you take these, you make them approximately uniform. And again, why do we do this? Well, ultimately, a few reasons. One is we're going to combine many different types of scores. As Josh said, if you put a ton of mass on one side, it's going to dominate the overall score however you weight it. So that's not good. Second, you want calibrated scores ultimately because we're statisticians. What we're going to do is look at a distribution of these p-values, right? So if you do Fisher scoring, you're typically looking at the chi-square distribution. And that'll basically tell you how you should rank, what's anomalous, right? So those are two reasons why you would want this. Now, let me tell you why that's not enough. So I call this kind of P-value calibration. I'm a forecaster. And anyone who studied forecasting, specifically weather forecasting, think of this, and I'll give you a technical definition in a minute. So everyone's faced with the weather. Okay, it's sunny today. Maybe earlier in the day, somebody predicted it's going to be rainy. Go bring your raincoat, right? Okay, well, that's binary at some point in time. Either it's sunny or it's not. Okay, but that's not how we do weather forecasting, right? It's probabilistic, actually. So if they say it's a 80% chance it's going to rain today. Now, depending on your interpretation of what that means, what's uncertainty, you could actually play that out in a few different ways and say 80% of the time, whatever that means, it should actually rain. Otherwise, it's miscalibrated. So that's how I think of calibration. It goes back to the actual output, whatever you're modeling, right? When I say X% of the time, it should occur X% of the time, whether it's an interval, whether it's a density, a quantile, whatever. And that's what I'm going to try and convince you guys of how we should think about calibration, even in cyber. So Josh kind of sketched that architecture diagram, right? So this is butchering that up. As I said, I'm not very good at showing a lot of pictures, unfortunately, but we have this massive vector, right? This massive vector S hat here, which does depend on t, by the way, whether you're doing sliding windows or modeling as a continuous time. It's a vector of a bunch of scores, right? Billions of scores. And you know, this kind of obscures the notation. These scores could also occur at different time points too, just to complicate things. Ultimately, though, we'll create some score, whether it's on a set of machines, per machine, per the kill chain itself. We'll create a score, and that's what we're going to alert on or rank on. And that's some function of this vector. And you know, the Fisher scoring is one function. Once we have that, we're going to do some type of thresholding or ranking, right? Technically, you're still doing thresholding of ranking because we don't show them everything. So you are thresholding in a way. Now, if we're ranking, you would expect the top to be the most anomalous, actually, right? Now, it's not going to be perfect, but again, if you look on average, the top 10 things should on average be the top 10 most anomalous things relative to your data generating process. Again, if that's not true, it's not calibrated. But ultimately, after we threshold, we're going to either subset a bunch of alerts to show or scores to show, or just one alert. I call that AAT. It's just an indicator. It's an alert, basically. And this is something people should pay attention to. This is anomalous, right? Ultimately, everyone in cyber is thinking about this is an indicator of something malicious. It's an attack, right? We're not just showing, per Josh's point, anomalous stuff. There's a lot of anomalous stuff. And that goes back to it's not useful. So that's what I'm trying to drive home here. Under calibration, you just think of calibration as a statistical exercise. You're modeling some signal. You're looking at, is your model specified with respect to that signal? It's calibrated. That doesn't mean it's good, right? So what I'm going to try and explain is what we should do. So ultimately, whether in cyber or we're doing anomaly detection in some other application, you have some latent process that often you don't get to observe, almost you never get to observe. So let's say z at t here. Again, it depends on time, and think of z as a vector. Need not be a scalar, right? In fact, I'll convince you in a minute, z is a function. But this is the indicator we're actually interested in. It's hidden. We don't get to observe it. But still, as statisticians, we know how to model latent variables, right? There's different ways to do that. So that's going to actually be the, if you will, the point of my talk. So how do we shift gears from thinking about just signals and the data around those signals to modeling this latent process? And per Josh's point, one thing we actually do pretty well at Microsoft is we have graders that give us FPs. They give us samples. So not all alerts are graded, but enough are graded. And yeah, they're noisy, graders may not agree, but we basically have probabilistic samples, and we know how to do with those. So that means I can't really optimize for Z because there's the false negatives, right? There's the unknown unknowns. But what I can optimize for is what we usually do. Well, this isn't true. We don't have perfect labels. We don't have all labels, but we have partial labels. The partial labels are coming from basically the TP, FP, or even we'll call them BP, benign positives. We have some indication of, was this alert useful, actually? So what I could model here, I can't model, unfortunately, the full distribution, because there's a bunch of stuff I don't get to see, but what I can model is the marginal distribution, right? I can model precision. And if you're in machine learning, just think this is some binary classifier. You could calculate precision. Semi-supervised learning, essentially, right? Now, we could talk details. How many labels do you have? Does it introduce more noise doing this? There's details. But think about, ultimately, if I understand precision fairly well, that tells me quite a bit of information I could use to start weighting scores, updating scores, at least monitoring the scores. And that's exactly what we're going to jump into. So quite a bit of notation. I've been told my notation isn't standard sometimes, so bear with me. But we're thinking of Z. And remember, a realization of Z, which we don't have, would be an attack, let's say. But Z is a function, right? You have some probability space. Think of Z as, if you don't know what random functions are, it's a stochastic process, right? So I could treat it that way. It's Bernoulli. It's going to take on 1 or 0. But it's going to do it in a functional way. So ultimately, its values as stochastic process will live in some function space, H. I use H because you should be thinking about stuff like Hilbert spaces, reproducing kernel Hilbert spaces. However, it could be anything. The math gets more and more complicated the more abstract we treat it, like a topological vector space. But point being, let's treat these as functions. But then we don't get to observe functions, right? We get to observe discrete samples. So then for those of you who are familiar with functional data analysis, you're probably already something clicked. It's like, okay, but we could create functional representations with discrete data. And that's exactly what I'm going to propose here. We have some set M. M is basically a collection of samples of precision. They could be samples actually of the TPs, FPs, but for practical purposes, let's say we have estimates of the precision. And we have some lawn vectors, and we have different points in time, right? Okay, so then how am I going to model mu? Mu here is basically my precision function. I'm going to model it conditional, of course, on some parameter, some probability distribution with some parameter. Here, though, my parameter is going to be a function as well. Okay, so you could already think this is like a non-parametric way to do this. Of course, I could look as just parametric. This is just a vector, even a scalar. And we'll get to that in a minute. And I'll try and convince you why I want to model things in terms of functions. But here's the problem, right? Ultimately, if I construct a good function, a representative function, I get sample paths from them, right? Sample paths conditional on my parameters and conditional ultimately on my discrete samples I've observed. Then I could actually start using these sample paths to update my scores. And that's what I'm going to talk about quickly next. So at the end of the day, you know, the SOC or even our threat hunters, they can only get through so many things. They have other stuff to do as well. So they're going to have a false positive rate or a tolerance on the number of false positives they could see at some point in time. There'll be some flexibility. Maybe they think in terms of averages, maybe not. But certainly, if you show them 100 things, you don't want 100 FPs. That's bad.
So just a quick question.
What's
the difference between a false positive and a benign positive?
That's a good question. I know a little bit about this, but not much. Okay, so a benign positive would be it wasn't actually an attacker. It was like pen testing. That would be benign positive. Does that make sense?
Yeah.
Perfect. Okay, good question. Yeah, maybe I shouldn't have threw that out there, but we do have that distinction for what it's worth. Oh, and also, it's a little more complicated than Bernoulli because they also sometimes put a known. They take the time, they grade it, but they're unsure, so they won't actually assign a label. We can still model it, though. It's OK. So I have two proposals here on how we translate kind of this random function of precision into how do we model it, right? And again, I'm being abstract. There's details in the appendix. Happily, I'm talk offline about how I actually modeled this. But OK, for the Bayesians in a room, I decided to have a Bayesian flavor. I'm indifferent, ultimately. I want to model uncertainty properly. I'll tell you one way to do that today. But let's say I'm ultimately working with a predictive distribution. It could be a posterior predictive distribution, but some prediction, right? So let's say I already have given a vector of alerts. That's A. So that's happened. In fact, that has to happen for us to grade, right? So it's already in balance. But anyway, well, as I said, if I know what this thing is, I could sample from it, right? So maybe you guys are thinking, oh, billions, how is he going to estimate these? Let's talk about that in a moment. Let's say I have estimations of this. I could certainly sample from it, right? And there's actually scalable ways to sample from a very complex distribution, so I'm not concerned about that. I could sample from it. And then, of course, I could start computing, Once I've sampled from this, I could start looking at conditional sampling, right? I could say, what is the samples of precision that at least exceed my threshold, right? I need at least this type of true positive rate. And that's what we care about ultimately. So let's say if I denote this by the restriction, like for those who are in math, that's why I have that notation. Now, my proposal is as follows, actually. So we're given kind of this restricted distribution. We're looking at some truncated distribution of samples of precision, right? My proposal is simple, actually. We redefine the scores, whether they're heuristics, whether they're distances, or whether they're actually p-values. Let's redefine them weighting based on that restricted or truncated precision. It's pretty simple, actually. I changed a little notation a little bit. I call these incidence scores, whatever. But if you want a compact representation, like at this point I have samples, right? And yeah, we can model the distribution, but something practical you could do is compute quantiles. And that's p-values are, actually. They're quantiles. So I get a quantile representation. I get the quantile at my true positive rate I'm looking at. And that's what I redefine as the score. It's actually not too complicated, if you will. Probably a lot to digest. Notation, granted, could be bad. But bear with me. Let's say this is making sense so far, and you have a lot of questions. How are we going to estimate, what kind of models, et cetera? We'll get there. Let's say this makes sense. Let's say we could pull this off. OK, so then I'm going to redefine what calibration is. And I haven't invented this. This is common in the forecasting literature. It's probably the only value I've added so far in Josh's team. But let's say we have future intervals. So we observe stuff up to some time point. What's my time point here? M, whatever M is, right? And I'm thinking of this as continuous interval. So there's some small epsilon plus some h steps ahead we care about. And what is this interval? So if I'm the SOC or I'm threat researchers at Microsoft, they're not looking at the grades every millisecond. That makes no sense. Grades are delayed, right? There's a lag. Humans are doing it, so they can't do it real time. So maybe this interval is something like daily or weekly or some higher or lower level frequency. But let's say I know basically the intervals I'm interested in, future intervals. I have samples of these, right? Or I'll get samples of these eventually. I could then compute under the model I specified, right? What's its accuracy relative to that? If I'm doing quantiles, it's really simple. Then I know what an accurate quantile is, right? That is basically to say the proportion of the time it actually exceeds my sample should exactly be at that quantile level, beta. And that's what calibration is in forecasting. Doesn't necessarily mean the forecasts are the best. That's not true. But it is it's not a sufficient condition. It is a necessary condition, though. If your forecasts aren't calibrated, then that basically means there's a bias in some form or fashion. And yeah, there's a bias variance trade-off and stuff, but most people don't want a consistently biased forecast unless, I guess, well, I won't even go there. So yeah, I guess my point is we should have whatever alerts we're producing, whatever scores we're generating, ultimately they should be calibrated in the sense that we're forecasting something, we care about future performance. It should be consistent with the data. That's all I'm trying to say. So that was a lot of talk. Let me get into, so that's kind of the preparation, probably more time than I wanted to spend. Actually, not bad. Let me try and formalize this a little more. Again, bear with me in the notation. Bear with me in constantly moving my head up and down. But yeah, so let's go back. Mu here is a function, right? It's the precision function, if you will. I'm going to model that as a distribution. So for those of you who studied functional data analysis, or even studied non-parametric Bayesian statistics, the first thing maybe that jumps out is Gaussian processes. That'll put a prior on functions. So we know how to do that. I'm not going to go down that route, actually. It's a beautiful route. People have done that. I'm going to go down an information theoretic route. I'll take us there in a minute. But we could do this. For those of you that know quite a bit about math, or remember at least your measure theory, I'm not claiming that we could put a density. I'm claiming we could put a distribution. A density may not exist in infinite dimensions. Talk to me offline if that makes no sense and you're interested. But anyway, okay, so this is what we're trying to head toward. And again, crappy notation, but just say I have samples 1 to t in this case, up to time t, right? And t in this case, literally, t could be anything. We get all kinds of snapshots. They're not regular time series snapshots. They could be highly irregular. But then once I've observed my last snapshot of the day or the hour or whatever, I could then talk about the future, right? Stuff I haven't seen is to come. And then I have 2 tasks or problems. Problem 1, well, there's a problem of mu too, but let's get to that. Problem 1 is monitoring. So before we update scores, one thing we do with heuristic IOAs, heuristic detectors, is they will degrade over time because eventually there are rules at some point in time, and the cyber landscape's changing, right? There's non-stationarity. So the easiest thing, to avoid customer pain might be to turn them off temporarily, or certainly revisit them. In order to do any of that, you need a monitor. The last thing you want is customers constantly telling you, like, oh, this is generating just FPs. I don't like this, right? So that's one problem hidden here. And I would argue it's important no matter how we do meta-learning, model selection, things are going to be wrong. So we need some mechanism to update us. So human in the loop's still important here, at least for now. And what is monitoring? I'm kind of formally defining that as follows. You have a function, the precision function of your future interval, right? Conditional on how you've modeled it. Those are those theta t's, including the distribution. And of course, conditional on your samples. Okay, so that's the monitoring problem. The updating problem is similar, if you recall my other notation. Once I have this, then basically I can conditional on that, right? And I come up with, what you'll see in a minute, is just a mixture. Okay, so if you pass me a bunch of scores and their precision is all 1, they'll get 100% weight. If the precision's all 0, it's just point mass at 0, it should get no weight actually, right? So then something's going to be in between. That's what this guy tells me. How do I model that? What's the probability of having a relative precision of beta? So then I quickly outlined some principles I kept in mind of doing this. One, if we're Bayesians, there has to be a choice of priors here. This is really important, by the way, because think about we're constantly creating detectors. Okay, that means you don't have much history. Even for detectors that have been around months, we're not grading everything. Still, a lot of sparsity. So that's really important, actually. Coupled with, of course, when you have priors, you should be thinking about your likelihood functions. Now, the red is basically my attempt to explain, as we go through this, keep these things in mind. Number 1, I actually want to model the uncertainty in everything. The uncertainty in my prior choice, the uncertainty in my likelihood choice. Why? Because if I misspecify this guy, these guys are going to pay. The monitoring is also going to be useless, right? So that's 1. 2 is everything ultimately is driven by these states. You'll see in a minute I'm going to propose a state-space model of some fashion. But these states, in these cases these are still functions, they should capture all of the complex dynamics in the system we want. So at this point, I don't want to assume IID, right? I actually want to understand what's normal, including the non-stationarity, including the spatial temporal characteristics in the network, right, of these precision. But I want to do it in an interpretable way. I don't want to throw deep learning, say, at it and figure it out for me, right? That's probably not going to work. It probably won't be robust over time. Certainly, it won't be robust with small data. Finally, in order to do any of this, I have to have some type of decent estimation, right? And what does that mean? Well, okay, it depends on what we're doing. Are we doing MAP? Are we doing MLE? But good statistical properties, certainly asymptotically, we should care about that. In the long run, it's doing the right thing once it sees enough data, right? But more importantly, it has to be easy to maintain too. Okay, so there's people like me or other people in Josh's team building this stuff, and I have other priorities too, and so we can't constantly be with, oh, your monitoring's not working, your updating's not working. So they basically have to be self-operating. So we need some type of robust estimation too. Now, before I jump into the next slide, one thing to keep in mind is we could actually decouple, to some extent, the monitoring and the updating problem. If you think about that for the minute, the updating probably has to be real time, but the estimation doesn't, right? That's going to save us a lot. Certainly the monitoring is not real time because people aren't real time. The monitoring is for people. So, first thing, and this is kind of what I propose as the meta-learning or meta-processes, is we're going to update these parameters, these functionals, if you will, that's what they actually are, random functionals, in a batch mode. Now that could be daily, it could be a few times per day. It certainly doesn't need to be streaming. In fact, let me explain, beyond the human capacity of consuming these, reviewing things, there's no way in practice, because I know people who are theoretically oriented could throw a counterexample, that mu is going to change that much. First of all, mu, precision, is some type of expectation. It's an average. It's not going to constantly shift from 1 to 0, assuming sample size is there and stuff, every hour or second. That's impossible. So there's no reason to actually update your parameters that fast, okay? Other than that, there's all the practical reasons why we don't need to do this. It's completely overkill. Hopefully that makes sense. Happy to argue offline. Second, okay, so there's a few use cases for monitoring, right? Maybe there's some strategic detectors that are really important, that humans actually, or enterprises, they're new enterprises, we really want to monitor them, make sure they're getting good value out of our product. So maybe humans also just want a dashboard, they basically want to be involved and look at a subset, even if that subset's in control, statistically in control. So control charts, right? Statistical process control, that's one use case. On the other hand, there's a lot of these scores, as we talked about, or alerts even, not even the scores, alerts. We shouldn't be wasting their time unless they're not calibrated, right? If they're probabilistically calibrated, basically, meaning we're predicting it accurately, we might want to inform them, oh, FYI, these things are happening, but this is where the updating side comes in. If we could do this autonomously, we could correct it too, and just leave them in the know. They don't have to actually take action per se. So that's kind of the two use cases I'm seeing with monitoring. Now, hidden under the covers, if you will, or maybe not, in order for this to actually work, and I'll show you in a minute, domain experts have to be involved here in practice. They're going to have opinions on certain types of non-stationarity isn't a problem. Well, here's a perfectly simple non-stationary case. You have a machine that's doing periodic things, periodic events, right? They don't probably care about that. That's expected. So yeah, and per Josh's point, and I've seen this myself, you're going to find really weird stuff looking at a large enterprise just due to chance. They probably don't care about everything. So they're going to have to give some input, and that's how you could actually encode it in terms of your prior too, if you want to take a Bayesian approach. So quickly, probably a lot of you have seen control charts. These are simulated examples. I'll show you some real examples in a minute. But these are simulated. So let me give you pretty much a mean variance, covariance, stationary process, right? With some noise. And let's say the blue, about 75%, is kind of our target precision, our expected precision. We want to have about 70, and I'm making this up, these aren't real numbers, but let's say for a given enterprise, on average, they should have a 75% precision in a given alert we're firing. Okay, so we have a yellow line maybe. That's like borderline, I'm concerned. The way I'm looking at this is probably a spike. This would be like a spike in FPs, right? Depending on its magnitude, like if it's only one machine, let's say in an enterprise, that's it, at one point in time, I might not be concerned, okay? Same with the red. Again, I might not be concerned. What concerns me is shape changes, okay? So this is stationary, which means I can model it, actually. I know what to expect. This one isn't stationary, okay? So I would say this is a probable concern because it's borderline. There's enough uncertainty here to say it might bounce back up. This might just be noise. So I could alert the people and waste their time, or I could hold off, get more samples, get more confidence, right? The other one, though, let's say at that point I'm pretty darn confident that's a problem. Actually, it's already bordering my kind of my worst case scenario of red. It's shifted, and let's suppose for the minute this is a long time scale. This is like a full year or something. That's not good. If I know it's a heuristic IOA, meaning it's static, that's also not good. So this, I probably actually want to raise a notification or update the scores. And I guess to close kind of the meta-learning process, that was the monitoring side. The monitoring side is basically kind of informing you. It's informing people, it's informing systems. The informing systems here is how do we update the scores now? Given I'm monitoring, I believe in my predictions, they're calibrated. How can I use that information to update my scores? All right, so I have these alerts. The alerts are conditional, of course, on scores and how I combine the scores. I get samples of those. And that's kind of what we have today. The samples really are just p-values, so it's just kind of a one number per alert. But let's say I have a distribution of those. And I do exactly what I proposed earlier. I could model now the precision, basically, of that alert. And then I could predict the precision, right, at some future time point, given an alert takes place. Let's say I could do that, and I get samples. Then effectively, what ends up happening, the final score, if you will, sample of scores, it's just a mixture. It's a finite mixture. It's what you would expect. And then, again, if you don't want to work with large amount of samples, scalability, space complexity issues, you could summarize it into a quantile, right? So hopefully, conceptually, this is kind of making sense, nothing too fancy. Kind of the remainder of my talk before we get into the application, and I guess the wrap-up, I'm going to talk about a proposal of how we model. First, just to not confuse anyone, I'm going to remind people what state space models are. I'm going to focus on a specific type of state space model called an innovation state space model, or a single source of error model. Maybe those in the room could counter, but well, why not multiple source error? Definitely talk with me offline. The good news is if you do these right, under certain conditions, they're actually more general than the multiple source of error models. That may not make sense intuitively, but I could point you to the math, actually. Under conditions, right, stability conditions. And why am I doing this? Because, well, I'm a forecaster. For those of you who've done forecasting, including state space models, you probably have worked with a common filter at some point. If you ever actually use common filtering in practice, you would see it often doesn't perform as well, or it's about on par with just smoothing models, right? Hence, innovation state space models. It turns out the innovation state space models, it's kind of a complete model family for all smoothing models, up to some point, of course. What I'm going to propose today is an extension of these. But let me quickly remind you what state space models are. So states are latent processes. We have some realization, right, that I'm thinking of as a sample path. That realization, maybe there's seasonality, but we don't observe seasonality per se. We observe sample. Seasonality is hidden there. There's maybe some changing level or trend cycles. These are states. Maybe there's an intervention. So for example, just because I was in retail forever, one type of seasonality would be a Black Friday effect if you're in the US. I'm sure UK has something similar. Promotions. Price wars. Okay, that would be an intervention or a shock to the system, probably temporary shock. All those could be encoded as states. Any type of change point could be encoded as a state. So I like state space models. They're a way to basically capture all the time series finite feature characteristics you could think of. I'll tell you in a minute, though, how we could do something slightly better. Normally, when you model these things, unless I guess you do full Bayesian and simulation-based approaches, MCMC-based approaches, things get complicated when you're dealing with non-Gaussian, nonlinear state space models, actually. There's ways to deal with it, but practically speaking, you run into convergence issues. Different things happen. So a discrete set of states may not be a very efficient representation depending on the type of modeling you're doing. You might need a large state space, right, and cursor dimensionality. If you want to do things multivariate, it magnifies, right? You could do this univariate. If you want to do multivariate, it's much harder. So anyway, maybe I'm digressing. But just recall, state space model. The key here basically is the state itself has the Markov property, right? It only depends on its most recent time point. Which is great about that is I don't have to store an entire history. So if I am space complexity constrained, I only have to store its most recent state. Now, I'll talk about something slightly more extensive we could do. I get a little nervous about that because you've made a model selection choice and now you're not quantifying your uncertainty in that. But there's ways to deal with that. This is just an innovation state space model. You'll notice maybe some non-standard notation. So, okay, remember just usually this is a YT or an XT. So bear with me, but conditional in the state vector here is XT. Mu T, remember, we get samples of mu T, right? So these are some realizations. And that depends on some probability distribution, conditional in my states. And if my probability distribution is highly non-normal, non-Gaussian, normally what you do is you have a link function, right? So you'll see in a minute, I mean, precision is what? Precision is a proportion. It's the number between 0 and 1. We obviously don't want to model it with a Gaussian distribution. But what you can do is you could take like a logit link function, right? That's something we tend to do with beta distributions. And why do you do that? You take that then, and you could have a nice additive model representation, right? And get you back to, in this case, a standard state space models. Once you've conditioned on the link function, then basically you're dealing with some type of function of white noise. That function can be complex, by the way. It doesn't have to be the identity function or anything. But that's an innovation state space model. And I gave a reference here for those who haven't seen this book, Forecasting with Exponential Smoothing, the State Space Approach. Rob Hyman and a few others. Good book, good practical book with some good theoretical results. Quickly, originally people used exponential smoothing. They used it as an algorithmic fashion, right? They didn't think of it as a statistical model. This was one way, and it was kind of before this time, to actually make exponential smoothing proper statistical models. I probably won't bore you with details of this. If you study, I've seen several nods, so the good news is people have probably seen state space models before. You'd be familiar with filtering, which is like updating your posterior distribution. And the nice thing here, I mean the punchline, if you will, is you start with a prior, right, before you have any data. You eventually get data, you get your posterior. Now, that becomes your prior, right? And you go through, I guess, the math, if you will. Usually this is some complicated integral, but we could sample from that in some way, depending on your choices of priors, likelihood function, and so on. Maybe you could get a conjugate prior, simplify the analytics, maybe not. But usually we could sample from this in some way. And filtering essentially is what type of estimation procedure do we do to update these. Now, I have an appendix that kind of talks about a few different estimation procedures I've played around with. But the point is, outside of the actual algorithmic estimation, the math is actually pretty straightforward. Not saying it isn't complicated. Now, see, might have to talk a little bit about this. So just think we went through the innovation state space. You should recognize, you can interpret them as functions, but they're not. They're vectors, right? States are normally thought of as vectors. Now, the states themselves, what I mean by that is the number of states, right? Like your level, your seasonality, your change points, they're all brought into some vector. The seasonality itself could be modeled as some continuous process, as in the level. But you get into problems, as I said, when you start dealing with nonlinear state space models. The number of states that you might have to grow the state space by, as I said, magnifies. So what's a way around that? Well, modeling it in terms of a smooth process. And this is where, if you've studied ARIMA models, you probably came across functional autoregressive models. I'm kind of borrowing from this, actually. So through smoothing now, I'm treating these as functions, remember. Mu is a function. and I have some distribution, which I'll talk about what is the distribution I chose in a minute. But let's say I have some distribution. And now theta is no longer a vector, a finite dimensional vector. It's an infinite dimensional vector. It's a vector of functions. Okay, how can I model functions? Yeah, earlier, those of you nodded about reproducing kernel Hilbert space Gaussian processes. You start thinking about the smoothness properties of these, right? If you're a Gaussian process person, you're doing it through the kernel or covariance function, okay? If you're, well, an equivalent way, let me say, of doing that is working with basis functions directly. So some people like wavelets, some people like splines, B-splines. I'm one of those guys, cyclic splines. Some people like neural networks. They're just basis functions, actually. Don't let anyone tell you any different. Tree-based models, whatever, you name it. They all do some type of smoothing, essentially. They have assumptions on how smooth the function is they're modeling. And that's all my proposal is. So now we introduce, I call it B here because of splines, but this could be an arbitrary basis function. Actually, I take that back. I think I chose B for basis function, but underneath I'm thinking B splines for I don't know, selfish purposes. So I don't change the state space model formulation. That all stays the same. The functionals, if you will, the basis functions don't operate on time. They actually operate on the states. So you still have states. You still have a level, a trend maybe, some type of slope. You have some change points. You have some pulses, whatever. You have a vector of seasonality. I often tell practitioners this: if you're going to do a periodic or seasonal ARIMA process and you're doing it in high-frequency data, a standard ARIMA doesn't have any regularization. You have to specify as many parameters, right, as you're modeling the time frequency. Well, okay, spline models, they do regularization. So that will actually handle that for you. So instead of staying, let's say we're looking at 24 hours, maybe you don't need 24 data points to model seasonality. Maybe you need 12, maybe you need 5. So that's the nice thing about the smooth properties. And then some fancy notation. I don't know what the basis is. It lives in some space H. Let's say I'm going to approximate it because I only have finite computing power under some finite dimensional span, right? Finite number of basis functions. And I'm going to take their closure, right, to make it complete space. So maybe the actual limit exists in here. And what I'm going to do, let's see, blah, blah, blah. Yeah, so the way I'm thinking about this is exactly how you would do time series decomposition. But I'm now decomposing into 2 steps, the states and the functions on the states. So that's all. I've just introduced an abstraction with functions. Of course, you could remove all the basis functions to, I guess, the identity function, if you will, or a simple function, and recover the innovation state space models. Now, why am I doing this? This is how I'm going to propose MetaLearning. So depending on the class of basis functions you specify, right? This will be extensible enough to start approximating any type of patterns that come up. So I don't have to assume a fixed seasonality pattern or a fixed nonlinear growth pattern. These things will evolve and handle that. So I would argue they're much more flexible than somebody sitting there and taking a long time to specify states and relying that those states basically are going to stay representative of the patterns in your network, and then eventually monitoring will tell you when they're not. This will be a slightly more flexible way to handle model uncertainty of the states. I'll talk about the last thing, and then we'll go to application on what do we do with this? So ultimately, these are just models of precision, okay? Let's say I have different basis functions because I'm not sure. Some are more efficient than others. Like for periodic data, maybe I'm going to use Fourier. For non-periodic data, maybe I'll use a cyclic spline, or not cyclic, cubic spline, or some type of local polynomial. So it's unclear what's the right choice of basis given the type of data I'm looking at, how much data I have, the uncertainty in the data, and so on. But before I go through all that, I still have to specify a probability distribution, right? Okay, so hopefully most people agree with me here. If I knew we were working with a univariate distribution that had no inflation, right, and support in 0, 1, then a beta distribution would be a natural choice. But it turns out, with precision, with IOAs, detectors, there's a lot of inflation. You might have, over the course of 6 months, you might have 200 data points, all of one. That's not uncommon, actually. You might have some, when I raise this to my management, they're like, oh, but anyway, maybe I shouldn't say that. There might be several months, all 0. Well, that's probably not good, but maybe they're still willing to do that if it doesn't fire often, right? Maybe those months are across years. They're not consecutive. Anyhow, you have inflation. So then I probably have to consider an inflated beta. And it's not unimodal. It's actually multimodal. So I probably need mixtures of beta or a generalized beta. But once I account for that, this is a pretty robust, flexible parametric distribution. Of course, you could try and model it non-parametrically. I would argue with that in practice because, again, often we're working with detectors with short history, right? So when you start computing quantiles just non-parametrically, I have found it's not as robust, actually, in practice. Okay, so I do all of this, and I have in the appendix the details if you're not familiar with mixtures of inflated beta distributions. But the maths work out pretty nice. The link functions are pretty standard. So an inflated beta distribution in this case, let's not say I'm worried about the mixture components yet. I'll talk about that in a second. I could reparameterize beta in terms of a mu. Mu bar here, be careful, is the mean. Normally you see beta in terms of A and B parameters. Reparameterize it in terms of mu and a scale parameter. Scale parameter is new. That's not the same thing as variance. Variance depends on mean for beta, but this doesn't. And then eta, or I forget my Greek, tau. These are now kind of the zeros and ones, right? And of course, I can increase the parameters of the type of beta distribution. And then I have associated link functions, standard link functions. So let's say I do that. And this last slide, maybe I'll spend 5 minutes on this, actually. This is probably pretty important. At this point, you could do whatever you want. You could do MCMC. You could do MLE. You could do mixture models in terms of the EM algorithm. You could do direct optimization, right, with some type of numerical optimization approach. There's all kinds of ways to do this. Remember, one principle is I want to account for model uncertainty. So again, if I wanted to kind of be full Bayesian, I'd probably do Bayesian model averaging. But let's say I don't want to do that for whatever reason. Again, we could talk offline of why. I actually want to do something that I know is theoretically sound, meaning it will get to the right answer eventually under some conditions that I know what the conditions are. I don't have to guess at the conditions so much anyway. What is that? So, okay, probably those of you who studied some information theory, you've heard about Kolbach-Leibler divergence, Hellinger distance, and so on and so forth. You've also, I'm sure, heard about information criterions, AIC, BIC, WAIC, and so on, DIC. Okay. Normally, those are treated in a model selection context, right? It's like, choose the smallest. What I'm going to do here, and I didn't create this, there's references, and this has been done in forecasting. The cool thing, I haven't found a single paper that did an anomaly detection. Please don't try and publish something too quickly, because I'm working on this. But anyway, happy to talk about this. What you could do is, some people probably jump to, I know, one statistician questioned me immediately, why KL? Okay, it's asymmetric. Well, I don't care about that, actually. So I have some family of basis functions and its parameters, right? And I'm saying it's flexible enough to, the true model in the sense of a useful model is in there, not true as in there's a true model. A useful model is in there to try and account for my model misspecification. How can I do that? Working with some type of information criterion. What I could do is I can make it relative to the smallest, right, or the expected best in terms of losing the least amount of information. So now I've made it relative. I could compute an information criterion for each model under the data, and I could compare that to the best one, right? I could even put priors on this too, if I believe I don't have enough data to do this. Some people do. And this kind of becomes a relative odds. It's actually interpretable as a relative odds, and you could prove that. a KKE did, actually. And if you renormalize this, like if you're thinking information criterion, right? It's like on a log scale, take exponentials, kind of normalize. What you end up doing is creating relative probabilities, right? These are interpreted as a relative probability of a given model having, losing the least amount of information, I guess you could say it that way, or having the expected best Kolbach-Lieber information. So given there's a good amount of math here that I believe, I'll accept this. Given that there's been some success doing this in forecasting, better than just doing averaging, sometimes more robust than full Bayesian model averaging, I'll accept it. And given I've actually applied it myself in a few contexts and saw success, I'll accept it. So long story short, I accepted this. This is one proposal I have on the table. It's how do we do those mixtures? We do them in terms of the KKE weights. That's the actual proposal. Yeah? Okay. So I'm going to wrap up with this. I don't know how interested people are in this or not. Again, just interest of time. I'm going to go through this kind of quickly. I will tell you what the application is so you understand it. Results and stuff, hit me offline if you're really interested. So, you know, I was talking to Josh about this at some point, like the notion of IOAs, is that a common term? Indicators of compromise, IOC, probably. I believe now IOAs are. If you don't know what an IOA is, just think of this as some type of aggregation of multiple detectors, right? It's an indicator of attack. It's kind of that signal of something hopefully malicious is going on, certainly something anomalous is going on, okay, at some level. So then all that stuff I just explained to you, beyond me liking math, was actually motivated by a real problem. When I was hired, one of the first problems Josh raised to me was, okay, we have these threat experts, engineers, monitoring IOAs, just looking at them manually, actually, in a dashboard. We have customers that sometimes complain and say, okay, the precision is a little low, right? Well, probably you could think now, Microsoft Defender Advanced Threat Protection has grown a lot. We have a lot of customers, right? We have a lot of scores, and in particular, we have a lot of detectors too. You can't go monitor all of them. So it's not scalable. That hopefully is clear. Moreover, not to be mean, but just in practice, most non-statisticians, even very smart people, just don't think in terms of uncertainty. A lot of people, like in forecasting, they think point forecasting unless they're trained. And of course, that naturally has a higher probability of being wrong or wasting time. You know, finding spurious results, chasing noise, these type of things. Well, we could help them as statisticians minimize that because we quantify uncertainty. So there's that. This is really important. You remember earlier we were talking about there's all kinds of complex spatial temporal dynamics. We might assume IID for certain detectors so we could scale univariate models. But as I said, if we want to start monitoring correcting scores, we don't want to do that because I know a priori that's not true. There's non-stationarity, right? Especially in the heuristic detectors. They'll degrade over time. It's just a matter of time. So I want to capture all of that. But as I stated earlier, I could capture anomalies in the sense that they don't occur much under some distribution. That doesn't mean they're useful. So even under the indicators of attack precision monitoring, or I guess reverse the other way, I want to work with the experts to kind of have a good idea of what is anomalous. Are we okay? I'll give you a kind of a silly example. Somebody has an intervention we don't record in the data, I don't see. The IOA looks like it's kind of trending down. It's a little noisy. But all of a sudden, over several cycles of sample grades, it's trending up. It's looking great. Should I raise an alert and be like, oh, this thing's performing great, right? Do something. No, maybe they'll pat themselves on the back and be like, great job. Maybe they want to know about that in terms of their monitoring, their fixes, but I shouldn't send a notification and panic people, right? On the other hand, if the reverse happens, it's shifting down, 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 and I could predict that's going to happen, that probably warrants a notification. It depends, but probably more likely than the first scenario. So that's what I mean by understanding what really is anomalous in terms of useful. And then finally, so I did an experiment. I looked at tens of thousands of weekly time series. Why weekly? Well, there's just too much sparsity in the data, at least at the time in the data I looked at, to do daily or certainly hourly. You know, lags of grades, only so many graders, that type of thing. Plus, I wanted to evaluate if this crazy model I had in mind is actually good. Is it useful? In order to do that, I need data to test, right? But I also need data to train. So it's the classic sample size problem. So I insisted on looking at, for this experiment at least, representative time series, some new, some old, but aggregating it to a level of which I'm confident at least that when I measure the results empirically, that's not likely just due to noise either. And then what was the goal? What was the goal of this study? So working with Josh, statistician, he insisted on whatever I do, it should be interpretable, so no deep learning. Well, no offense again to the deep learning people. It should be accurate, of course. He didn't hire me to be inaccurate. Amazon, for example, has this quote, "all right" a lot, and my wife will often tease me, "oh, you're around a lot." And forecasting, we're often wrong. I've lived with that, but Josh doesn't want me to be wrong a lot. And then ultimately useful. So I could have a kind of an accurate model. I could accurately predict, for example, there's no change, and we're going to trend up. But if I'm not accurate in predicting it's going to trend down, it's not going to be very useful, or shift down. So those are the goals. Okay, and I'll wrap up here in a minute. So these are real patterns. I had to mask what are the IOAs, what are the machines, orgs, confidential information, right? But these are real patterns. Some people were like, whoa, that's amazing. I guess I won't mention names. This is kind of a classic stationary, if you will, and just treat the, this is time, just to be clear, and this is precision, okay? Sampled precision, I'll tell you that. And treat this as a pretty long time window, right? I'm showing you detectors that ran for a long time, right? We collected a lot of data just to see patterns emerge. This one's behaving fairly well. And let's say it's behaving at a mean level of which is acceptable. So they're not very interested in that. This one, it kind of had and the lines are kind of basis functions. And you know, there's all kinds of basis functions behind there. I have them in the appendix if you're interested. But let's say this is like maybe a low S basis function or maybe a dampened exponential smoothing basis function based on what I'm looking at here. Or some some basis function. And you could see, like there's a few ways you represent it. Maybe I was kind of fluctuating here and then went like that. I'm doing a smooth approach. But bottom line, there is a shift. There's a shift in the mean here. That's not great. So if I hid this here, right, and let's say I'm going to predict at some point with enough data, is this going to continue to happen? That's what we really care about. If it was going to shift back up, we didn't have high confidence it's going to continue to stay like this, I'm going to waste time. Long story short, I could tell you we were pretty accurate in predicting this stuff. I'll show you results. But anyway, kind of a dampened trend. There's multiple shifts, things going up and down. That could be noise, could be sensitivity to basis. But the bottom line is it's not like this, where it's completely went down from where it was before. It's kind of hard to tell. So maybe that one isn't so concerning. It's like a temporary thing. The random walk ones, they're certainly non-stationary. They jump around a lot. They have interventions, so large FPs. I guess depending on the mood, if you will, this may or may not be a useful anomaly. Why? Because if it really is a random walk, you expect it to be mean stationary, right? So not much you could do. I would worry, though, if it's a random walk with some type of, well, anyway, I won't get to that. Step functions, those are worrisome. Certainly worrisome, right? We're here, and now we're way down here, and that's been like that for a long time. And then if somebody goes and looks at that, they find a bug or something, definitely worrisome. And then these type of drifts, improvements, fixes, they're interesting. So for example, the engineers wanted a statistical way to quantify that this improvement isn't just due to chance, right? Under some model over here, you're very unlikely to see a lift of this, right? We want to quantify that for their own confidence. So that could be useful still for statistical modeling, but not for alarming people, if you will. All right, so quickly, that earlier model formulation I told you, the inflated beta-binomial, different basis functions. What I did is I looked at a bunch of time series. I looked at groups of time series. What do I mean by groups? Hierarchies. It's hierarchical. We have different types of machines. We have different types of enterprises, different types of detectors, right? Some are for reconnaissance. Some are for exfil. Some are for lateral movement, et cetera. So you have all these hierarchies. What I did then is kind of a classic bootstrapping time series cross-validation, if you will. I fitted a model. I predicted in some out of sample. I did that a bunch of times across a bunch of groups. And then what I looked at is the randomized quantile residuals. So under the model, right, I do the probability integral transformation. I transform that to a normal distribution. And then relative to the theoretical quantiles of a normal, it should look pretty good most of the time, and it does actually. In fact, in my experience, it's kind of rare to have such a nice QQ plot, certainly over a large sample size. Of course, it's not perfect. Probably don't expect it to be perfect, but it's decent. So there's that kind of like the statistical diagnostics, and then there's the practical results. So I already talked about how we measured accuracy. Here, essentially, remember I'm kind of doing a mixture model and I'm ranking, so there's probabilities of it being stationary, non-stationary with an upward drift, a step change, and so on. So I have these relative likelihood scores, probabilities of them taking on these shapes. What I could do then is set, I could look at their raw scores, okay? So think of these as now p-values, just like we had before, but these are p-values of shapes of precision. And I did two things. We did the out-of-sample testing and just looked at relative likelihood out-of-sample and verified the models recovering the data. And then we did real sampling where we looked at known IOAs that were problematic. People agreed in advance this is a problem. Some were unknown too, which is the fun part. But all of these over here, really high p-values, they're all not anomalous. The red are anomalous. You could see there's one FP here, right? It's not perfect. And then you could still argue these scores are maybe a little too low, right? These are not false positives, so it depends on how you control it, your control rate. This, I would say, is probably okay. Certainly these are okay. But yeah, it did pretty well. And then what I did is I had a big choice of models and basis functions. I can't get into details, I guess, because I'm out of time. But you could think about kind of the standard if you just use ARIMA-based models with model selection. You did kind of the innovation Statespace model family, kind of the classic EWMA Q-sum, random walk models, binary segmentation models. They're not as good. This is actually the probability of these getting selected as the best model, right? And I'm showing you relative stuff because Microsoft confidential and so on. But the best models were these EWMA basis function models, which is what I was proposing, kind of the functional state space models. And there's different choices of basis. There's one that actually does full hidden Markov models with the functional EWMA. That's really expensive, as you can imagine, but it's a really good model. Anyway, so conclusion. Okay, so for one, I'm kind of working with Josh and the team to see, can we release some of this open source? Can I give this to like Imperial College? They could start looking at it. So I have a prototype of these functional smooth beta models of what I call them, I guess. And it seems to perform pretty well on the data I've looked at. I've looked at other data, but so we have that. We do have, so my leadership has promised me that we'll implement this at some point. We haven't yet, but we'll get there. And I'm not an engineer, by the way, so I'm not going to implement things. But yeah, this thing accurately identified change points. And it was relatively better than the models I tested. I'm not claiming I tested all models out there, of course. But all the standard ones I could think of, our packages readily available, stuff I knew about, it's better. Right now there's a POC, proof of concept, running where we're going to evaluate these to update heuristic IOAs. That's the next step. So that was all the monitoring problem. The next step is updating these scores. So I'll be doing that when I get back to Redmond, I think. And then let's see, extended capture. Yeah, so what I like about this approach, the basis functions, they're extensible, right? So it's just a general framework. Any statistician could come in, include wavelets, include some type of spectral decomposition, include their Bayesian procedures. You could technically swap out, it's modular. You could swap out the information theoretic approach with full Bayesian model averaging, with some type of non-parametric classifier. So I really like it's modular. It should be quite useful. Now, a lot of limitations. In fact, I had like a page or half a page limitations. I thought, okay. So for one, I talked about there's these hierarchies. Right now, we're not inferring the hierarchies. It's kind of subjective and domain knowledge driven. I like to model uncertainty of that too, but we're not. So full disclosure. It's also very sensitive to the most short detectors, right? Of course. We assume some exchangeability in the hierarchy. That's not always true. Space complexity. So behind the scenes, if you look at my appendix, I do some dimensionality reduction stuff. Because remember, when I'm doing this mixture model, I need not choose the best model under MLE or MAP. I actually might have many representations. Think of a posterior, but many posteriors. So space complexity could get crazy. So you probably have to do some type of dimensionality reduction to keep the CS people happy. And I have ways to do that. Right now it's just batch estimation. It'd be cool to have a full basis function approach online. Interested in collaborating with that. Let's see. Right now I have one multivariate model, if you will, a bunch of conditional models, but no full, well, long story short, they're mainly univariate time series models, right? So it's going to miss stuff like the higher order interactions, cross-dependence, this type of thing, cross-correlations. The argument is the mixture will capture that in a relative framework, but room for improvement. And then finally, I have seen the beta-binomial or beta-inflated distributions. They're also not quite handling like really extreme multimodal behavior. Sometimes there's these crazy pockets of dense shapes. Trying to learn finite mixtures of those I've seen as rather noisy. So there's probably something better we could do. And then last slide. Vision, right? So for one, I think someone asked this earlier, how do heuristic detectors integrate into our anomaly detection system, our architecture? Well, the idea here is the monitoring and the updating is part of that system, right? So that's one. I have a vision. So I looked at IOAs. I looked at several other things since I've been in Josh's team. I want to monitor everything. So you know how Josh said model everything? I want to monitor everything. So that's kind of mine. My more ambition is complete auto-anomaly detection with MetaLearning. Remove the statisticians, including myself. I did that successfully at Nintendo, by the way. I actually created a bot and removed myself. It's still running. It's still forecasting. It's still doing better than the subject matter experts. So I'll tell you it is possible. Okay, and then research. So one, there's kind of this graphical modeling we could do. I didn't do that. It's primarily univariate modeling. That could be interesting outside of the hierarchies. Other basis functions, so work with people who like wavelets, for example. I wouldn't mind partnering with people who are in love with deep learning either. It's just another basis function to me. It will increase complexity and you'll lose interpretability, I suppose, but it would be interesting. Certainly improve the estimation procedure. So in the forecasting literature right now with MetaLearning, one popular approach is training like, you have a bunch of forecast models, time series models, machine learning models, and then sitting on top of that, a MetaLearner, a classifier, learning how to do model selection or ensembles. So that's kind of some type of non-parametric learning. Think random forest, think deep learning, however you want, or some type of Bayesian approaches. I think that would be fun to play with. I haven't done that in this context. A real passion of mine, for those of you, again, who study forecasting, you might have heard about hierarchical and temporal reconciliation. This is learning models at different frequencies through time or at different hierarchies and then combining them, leveraging all possible information. I've seen this work very well in practice in retail. I'd love to apply this idea in anomaly detection. And then finally, the EWMA-based models, the smoothing-based models, I didn't do any type of dynamic learning, so that's one caveat with the innovation state-space models, right? Because you only have a single source of error, they're not varying coefficient models. So one thing we could do is include forgetting factors, something Imperial College knows how to do very well, and make them dynamic smoothers. Instead, I basically have these large grids of smoothing parameters I pass to the mixture. Okay, and then last, Thank you for your patience. And we are looking for collaborators. If this was an interesting talk, some of the research, definitely feel free to email me or Josh. Thank you.
I'm not Mark Bride as much as I've aged really badly in the last hour. So, questions, comments?
Did I lose everyone? Is this too obvious to people? Time to go to the pub, maybe? Pub.
No?
So you've got your prediction that there's like a trend in the precision for like a particular detector.
Yeah.
And you've got some confidence that that it is a trend, that it is some
That's
other behavior,
right.
etc. Right? Is there kind of like you talk about like hierarchies in terms of the variables you're modeling, but like is there a kind of hierarchy in terms of the detectors, or like some kind of I mean, not necessarily correlations between what the detectors predict, but in terms of their behaviors? Because some of the
Yes, absolutely.
I just mean some of the times in the past we've tried to do kind of similar modeling in one of my previous places and trying to detect different types of time series, and then you've got a difference between, hey, look, there's like 10 different types of behavior, but like you're pretty confident, but maybe it could be something else.
Yeah.
And actually, if you put like a prior to say like I think there's probably only 5. That it's actually probably the second one down because there's and maybe in this case there's causal factors and you think it's actually there's several trends going on all because of the same reason.
Yeah, and that's a great question. That's one reason I'm doing mixtures to try and account for that. And there is a hierarchy even within detectors. So we have categorizations of detectors, both within the kill chain as well as the different parts of telemetry, at least the detectors we're building at Microsoft and our team, we know like the process trees they're modeling. So you could account for that hierarchy actually. It gets challenging, large dimensionality if you will, but yeah, I would say you get, you certainly increase your statistical power doing that. Yeah, good question.
Is there any possibility that some of the curve that you are observing is incomplete? Then how this model is going to incorporate?
Yeah, excellent. Another good question. I was hoping somebody to ask that. So yes, absolutely. A lot of these are highly irregular, and as I said, or maybe I didn't make this clear, the sampling we do of alerts and the rate at which we do them changes, right? So to account for that kind of the holes, that's where interpolation with spline functions is very useful. So that's one reason I chose basis functions. Yeah, seems to do fairly well. I won't lie to you, of course, trying to extrapolate far doesn't do very well. Fortunately, we're not interested in really multi-step ahead forecasting, like a few points ahead, and the points usually are weeks or maybe 1 month, not very far in the future. So I don't have to do too much extrapolation. Yeah.
I have one more question. Is there intrinsically, are you assuming that there is an underlying Gaussian process? And
no, so that's also a good question. What I do is I assume the following. So a random function with the correct choice, if you will, or a choice of a distribution and a link function will have a decomposition into a mean or a signal and a noise. The noise I assume is a Gaussian process. I model that with different basis functions, right? Different covariance functions. All the ARMA processes, squared exponent, basically any type of stationary process and some non-stationary just in case it wasn't captured in the mean. But no, I don't assume that.
Thank you.
Yeah.
Okay.
I was just wondering, how possible do you think it would be for an attacker to kind of trick you into recalibrating your scores in a way such as to hide their attack behavior from raising alerts?
Yeah, it's a good question. It's possible, right? So I haven't observed this, not to say they're not doing it. In fact, kind of in certain other applications, we've experienced this, like we call it anti-tampering, where our sense agent, the client that's collecting telemetry, attackers could attack that, right? So we've observed some of this stuff. I haven't observed it so much, or at least I don't know that it's impacting this. Now, let me try and convince you, or at least sway you a little, on how this could try and accommodate that. So for a given time series, or a small set of time series in a hierarchy, they could. I think it'd be very unlikely for them to do it across hierarchies. And that's how I try and account for that in these hierarchical priors, basically. Again, it's imperfect, but that's one way, is to try and, as I said, increase statistical power of pooling information together. Yeah.
See, following from
You could use the microphone.
following from that, is there not almost like the lulling people into a false sense of confidence in that just loads and loads of stupid, unsuccessful attack, all of which failed because you caught them,
Yeah.
would actually lull your system into biasing its weights, such that when the different sort of attack happens, it's so confident that it's passing the other attacks. And this is a purely automated system. Obviously, your domain experts would spot such a thing.
Sure.
How do you alter the system to cope with the fact that one hopes, well, actually one observes, that nearly all the attacks on a big corporate fail?
Yeah, I don't know if this is a good enough answer to that, but the hope is through incorporating many basis functions. First of all, with these information theoretic mixtures, if you have a really large model family, it's unlikely to have like point masses for it to overweight a certain class of non-stationary models. For not stationary, definitely that will happen, but for non-stationary, no, because there's so much uncertainty. So if anything, think about this. When we're doing p-values, right, it's conditional on a null. So you have some sample paths from some model. Imagine I have sample paths from M models, a large family of models, okay? And as you know, once we start going into infinite dimensions, we could reproduce patterns easily with many types of bases. So the hope is that inducing that additional uncertainty will account for that. I don't know if that answers your question, but you basically enlarge your model space. So you're not gonna have point mass weights basically on any one model.
Gotcha. No, it makes sense. Yeah.
One more.
These are great questions.
You know, you'll regret it if you don't get it out now. You'll be going home. Oh, I wish I'd asked, and you'll never get the chance. That's now.
So we work in the IoT space, and we try to make the so-called smart and trusted dust more secure, so that all the data comes in can be authenticated, because we were extremely concerned of data sleepers trying to simulate normal behavior in order to train models. So I don't. I'm sorry, my maths is not as good as it used to be. So I'm afraid you have lost me when you talk about cross hierarchy and also the different normalization of noise. How would an adversary look at establishing different norms in order to hide? So it's the same question as the previous question. I just do not understand enough to say that if you are publishing the model, if you're publishing and open sourcing the workings of how you are extrapolating for anomaly detection, how would someone go about doing it?
Oh, okay. I think I understand the question. So keep in mind, this framework is kind of decoupling, if you will, the anomaly detectors themselves. So I'm not claiming of publishing, in fact, we wouldn't. We have all kinds of scorers out there, detectors running. There's some in our team, there's some in Azure, there might be some external. Customers might send us some. So I'm not talking about modeling the detector scores or understanding the detectors. I'm talking about modeling their performance, right? And keep in mind, some of these are dynamic too, so that also makes the modeling imprecise, if you will, right? Their performance is updating too, some are learning. So I don't know if this gets to your question, but basically we're not disclosing at any point what are the anomalies. What we'd be disclosing is how do we learn how to update the weights of the scores based on their performance. And there's slight nuance there, right? It's not actually directly going to tell you how it's doing it, especially if it's dynamic, because it'll change too. So I don't know if that's so much a big deal. I think it'd be a big deal if we released, of course, all of our anomaly detector code, but I'm not proposing that. I'm proposing just releasing the MetaLearner, basically, or how you should monitor. Yeah. Please.
The advantage that we have is that we know it's normal, right? And we know that across many organizations, and that's the thing that the adversary doesn't know. And so they can try to game us in certain ways, but what we've seen is, we've only seen this academically in that we've tried to game ourselves. And what we've seen is that it's really hard to do that without triggering some other behavior. That is, when you're trying to learn what's normal about the network, you're introducing other signal that we can detect. And so with the complex ecosystem that we're aware of, including other organizations and the threat intel that we have, you know, that we have quite a orthogonal set of capabilities to try to calibrate and any one detector that they may be trying to train. Is we have lots of other ways to do it. So you could think that our job ultimately, and this isn't very sexy, is to create a list of 1 million things that they better do right, and if they mess up any of them, we're going to catch them. And that's quite hard to do at the end of the day. So maybe that helped.
Thank you.